Okay. So last time, we learned about how to implement the object detection algorithm using the CNN architecture. Okay, so RCNN, that's the simplest way to implement the object detection algorithm using the CNN. I mean, but there are plenty of bounding boxes. If we apply the sliding window approach, this becomes impractical. So the researchers are thinking about how we can extract some small number of bounding boxes. Okay, that algorithm is called a selective search algorithm. So we only extract bounding boxes for this amount of number, and then extract for the extracted patches, we will apply the CNN architecture to classify those patches according to their semantic algorithm, and R represent the regional CNN. Okay. The first RCNN, they are improving this RCNN in the two aspects. Okay. So first, they are try to reduce the time complexity because in previous RCNN, we have to apply CNN multiple times. Okay. I mean, number of bounding box times we have to apply CNN. But here we can only apply CNN for the whole image and extract the two-dimensional feature in the middle, and then apply the ROI pooling to make the extracted patches, their features into the fixed dimensional vector. Then we apply FC layer and linear layers and nonlinear layers, and then apply the two types of loss functions to train this overall network. So now the entire network is becoming end-to-end trainable. Okay, so the first input is now the whole image, and then I mean the overall operations are becoming differentiable, and we can map it to the final output and then apply the loss function. So now the architectures are becoming end-to-end trainable, and then we can train them. Okay, but previous somehow in RCNN, this part, applying this selective search algorithm and extracting these patches, that part was not differentiable. So this was not end-to-end trainable. So the accuracy in fast RCNN is also improving. So when doing the object detection task, even humans uh, also need some of the contextual information from the whole image when classifying some of the patches. So the fast CNN is now using that kind of context information because the 2D features in the middle is giving some, how to say, giving some information from nearby pixels. So that's similar to what humans do for object detection task. And faster CNN that is further improving the speed and the accuracy, and they are solving the bottleneck in the region proposal algorithm. Okay, so in faster CNN, the selective search algorithm is separately applied, but still that is not optimal for the ICNN architecture. And so even because of that, in the last part, we are improving the bounding box information as well. But here, we explicitly estimate the bounding boxes from the 2D feature map and using that as the bounding box information for further steps. Okay, so by doing that, we can reduce the time complexity of the selective search algorithm, at the same time, remove the heuristics and make it optimized for the entire training. So the accuracy is also improved. So this is the summarization of that accuracy and time. So fast RCNN, the time is gradually reduced and their accuracy is also gradually improved. Okay. So far we reviewed the two-stage algorithms. They are called as two-stage algorithm because they first infer the bounding boxes and then classify those bounding boxes. But YOLO, they are called as one-stage algorithm because they jointly, simultaneously estimate the bounding boxes and also the probability for the regions, okay? And then they apply NMS algorithm, non-maximal suppression algorithm, to filter out unnecessary bounding boxes, okay? That's the YOLO. And this is the YOLO architecture, okay? So even though the pipeline could be summarized like this, what actually they does is training this entire architecture. So their output looks like 7 by 7 by 30 dimensional vector array because their 30 dimension is represented having some information like this, two bounding boxes information, and the probability for each region. As they are having 7 by 7 as the dimension because that is obtained for each subgrid regions. Are you guys following this? Okay. And also this architecture is end-to-end trainable. So by training this architecture, we can, achieve this output and then apply NMS algorithm to filter out bounding boxes. Okay, and slide is summarizing why we need five-dimensional vector for one bounding box. Okay, so their center position, width and height, and confidence values we need for one bounding box. And then in the YOLO algorithm, we estimate totally 98 boxes from the whole image. So because there are 7 by 7 grid in the default YOLO version 1 algorithm, and also for each grid, we are estimating two bounding boxes. So there are 98 boxes estimated in the default YOLO version 1 algorithm. But I mean, the number of bounding boxes in the YOLO version 1 is quite small. So if there are objects, I mean, if in one image, if there are more than 98 number of objects inside, then this YOLO suffers to capture those additional objects. Okay, so for example, in the image, there are, for example, 500 objects inside. Okay, then they can only capture 98 bounding boxes and missing all other objects. So that's basically the limitations of the YOLO. So in the last of previous lecture, I told about the recall and precision. Okay, we will tell about that. So YOLO, seemingly, this is what we learned last time. So here you can see YOLO version 2 and YOLO, their precisions are not bad compared to the RCNN stream algorithm. At the same time, they are very fast. Okay, that is the strength of the YOLO algorithm. But when we think about the recall, then YOLO is still weak. Okay, so what recall means is, so this low recall is the main weakness of the YOLO algorithm. And this slide is summarizing what recall and precision means. Okay, so I mean that's two important measures for in general, evaluating the performance of the AI system, and especially is important for the object detection algorithm. So measuring recall is measuring how much ground truths are covered. Okay, so for example, mm, in the image there are 10 objects. Okay, and we are trying to if the AI system they estimate bounding boxes like this, then the recall might be 50%. So when calculating the recall, uh, number of predictions over number of uh, uh, not prediction, number of correct prediction, number of correct prediction over number of GT, ground truth. So now there are four objects in the image, but we only captures the two objects as correct. So now the recall is becoming 50%. That's the concept of recall. And the precision means uh, the precision becomes like this. So number of total prediction over, number of correct prediction. That's the precision, okay, right? So this is the difference between recall and precision. So, here I have two figures, okay, and um, I mean, if we say, if some system, AI system, I can, we can view this as the humans, okay? So, don't know why, okay. Mm, let's say a person who speak a lot, okay, who speak a lot, normally, let's say this person is having the high recall, okay, say, uh, if someone who speaks a lot speaks, sorry, she speaks a lot, then there will be high probability to cover the ground truth. Okay? So if we predict, if our object detection algorithm predicts lots of bounding boxes, then there would be high probability to predict the correct bounding boxes, to capture the correct bounding boxes. Okay, so if we estimate lots of number of predictions, then it tend to have the high recall, okay, high recall. But in opposite way, it can, their predictions could be, I mean, how to say, even let's say they estimate 1,000 number of predictions, then if there are only four ground truth bounding boxes, then among these 1,000 bounding boxes, most of them will be wrong. Okay, so if some AI system predict a lot, then they can have the high probability to cover up the ground truth, but there's also at the same time there will be high probability to how to say, infer wrong predictions. Okay, so in this time they will have less precision. Okay, so precision and recall, in this manner they have some trade-off. Okay, if AI system, if some system, even humans, if they speak a lot, then they may cover up some true news. Okay, uh, let's say she speak a lot, and for example, in daily she speaks, how to say, 5,000 news. Okay, then among these 5,000 news, some may correspond to the true news. Okay, but remaining will be false. Okay, so that's similar to the AI system. If AI system predict a lot, then there's high probability to intersect with the ground truth, okay, which means the samples could be correct, okay. So there are high probability to cover up, capture all the ground truths, but the remaining predictions might be wrong. So, those kind of system may have high recall, but have the less precision, okay. And the other way, for example, these persons who speak less, okay, if they speak less, uh, they may have the low recall, which means, for example, if there are full number of ground truths, but because they are predict less, okay, they are predict less number of output, so they can only cover up two bounding boxes. Okay, so because of that, they are having low recall. But when calculating the precision, the total number of predictions are two, and also their correct prediction is also two. Okay, so if they predict only two output, and those two outputs are correct, then their precision becomes 100%. Okay, but in the recall, because they can cover up only two out of four ground truth bounding boxes, they only have 50% recall. Okay, so that's a trade-off. There are some trade-off between this precision and recall. So we have to simultaneously consider these two measurements carefully. Okay. But the thing I want to tell you is the YOLO algorithm is more likely to this person who speak less. Okay. They are not telling much things. So in the aspect of the precision, their precision could be very good. Okay. But in the aspect of the recall, they are not very good. So because they are predicting a very limited number of bounding boxes, for example, 98 number of bounding boxes, if there are more than 100 objects, they will be missing those objects. Okay. So as I told you, in the later versions of the YOLO algorithm, I already told you that YOLO now having version 12, okay? So they are the main feature, maybe there could be another features, but their main features are increasing the number of bounding boxes, okay? So they want to try to keep a balance between the precision and recall, because the earlier versions of the YOLO, they are focusing on only the precision. Okay, that's the review for these CNN-based algorithms. And then we will move to the transformer-based algorithms. Okay, so until 2020s, until 2020s, the CNN prevailed. Okay, so it starts from 2012. Okay, before their shallow learning algorithms had been prevailed, but in the year of 2012 to 2020, the convolutional neural network was the one of the successful deep learning algorithm. But nowadays, people are replacing the CNN algorithm with the transformer-based algorithms. Okay, so it originally starts from the natural language processing domain. Okay, so in the year of 2017, the first transformer architecture was proposed in URIP's conference by the Google researchers. Okay, so this original form of the transformer was proposed for NLP data, but now people are using this transformer gradually more and more for the vision and other modality tasks. Okay, and they are composed of encoder and decoder structure. So I will tell you how they are constituted. Okay. And nowadays, you see, you already heard about this GPT. Okay? We always use this GPT for many, many tasks. We are gradually increasing this application of GPT, maybe ChatGPT. Okay. Later, we will also see about this GPT. Okay. GPT is abbreviation of generative pre-trained transformers. Okay. So you can see that GPT is also using this transformer network as the basic unit. Okay, and also before GPT, there are lots of how to say foundation models in the NLP domain, and one of the competitor for this GPT was the BERT algorithm, and they are also using the transformer as the the core algorithm. Okay. So, but these are for NLP application, natural language processing applications. And we will first review how this transformer was originated for the NLP tasks. And then we will see how we can use these transformers for the computer vision applications. Okay. When try to understand this transformer, you first have to understand what types of neural networks have been used for NLP domains. So, CNN, you already now know that CNNs, their inputs are suitable for processing the images, which means the two-dimensional array. Okay? They are applying sequentially applying the 2D convolution operation and then flattening it and apply the linear layers. Okay, that's the structure of the CNN, and that is actually suitable for processing the two-dimensional arrays. Okay, but NLP, natural language processing, that's actually dealing with some one-dimensional signals, which is called as word. Okay, so it actually deal with real languages. Okay, and language does. The basic unit of the language is the word. Okay, so they are based. They can be basically represented as some sequence of word. Okay, so uh, in NLP domain, I want to say that the main signals are one-dimensional sequence. Okay, so dealing with proposing some proper method to deal with this one-dimensional sequential data has been the main how to say topics in NLP domain. And RNN, this R is representing the recurrent, okay, recurrent. RNN was the basic neural network structure for processing this type of one-dimensional sequential data, okay. And they can be represented like this, okay. And basically they are having a linear layer, okay, here. So maybe this block is representing the linear layer, and also they can add the nonlinear layer like the sigmoid. Okay. This is hard to understand at once. So I will, actually, we can redraw the overall figures like this. Okay. That's actually the same figure. Okay. And this is the linear layer combined with the sigmoid function maybe. And from the first input, okay, so basically in natural language processing, they are a sequence of the word. Okay, their input X is composed of multiple sequence. Okay, for example, like this. So each X is denoting one word. Okay, you can think it like that. Okay, and for each word, we may have to estimate one output for each input. Okay, so that's what these neural networks are doing. Uh, these inputs are not independent. The elements of this sequential data is not independent each other. So they are having some, sharing some context together. And in RNN, they are modeling this type of contextual information by transmitting some of the information, contained in when processing the previous input's output, they are extracting some features for the first input, okay? And then they are, transferring that type of contextual information to the this neural network, which will process the next uh, input, okay? And when outputting this H1, which is the output for the second input, second element of the sequential data, we also consider the sum of the context transmitted from the previous input, previous process, okay? And then we transmit again for next output prediction, and also transmit it for, uh, until we meet the last element in the one-dimensional sequence, okay? So this is the RNN architecture, okay? And we can redraw it like this, okay? This type of thing, we can draw it like this, okay? But the thing is, here again, the vanishing gradient phenomenon appears, okay? So in previous CNN training, we also meet this vanishing gradient phenomenon. And when the CNN architecture, their depth is becoming longer, the deep learning algorithm, their depth is becoming deeper. If we stack more than 20 layers, uh, because the gradients are becoming vanishing, eventually goes to zero, okay, because their scale is very small. So if we stack more than 20 layers, the training was not becoming stable. So we remedy this using the residual connections before. You may remember that, okay? Similar phenomenon is happening in this RNN algorithms. So if we input more than, how to say, I'm not exactly sure about the exact length, but anyways, if we input very long sequence data, then this RNN suffers from uh, making their gradient stable. Okay, so RNN algorithm, they are having limitations in this point. Okay, so if the sequence is getting longer, their gradient is not becoming stable because of the vanishing gradient. So the entire RNN is not becoming, their training is not becoming stable. Okay, so because of that, the LSTM, the long-term short memory algorithm, has been introduced. Okay, there are several algorithms to deal with the problem of this RNN algorithm, but LSTM, that is, one of the popular algorithms that successfully deal with this vanishing gradient problem of the RNN. Okay, and their idea is, um, they explicitly control uh, what to forget and what to retain. Okay, so that's actually the uh, I mean the strategy proposed in this LSTM algorithm. Okay, so because they are I mean processing the one-dimensional sequential data, basically they are inputting this x of t, which is the t's element of the one-dimensional sequence, okay? And this is becoming the output, okay? Okay. So to reduce the amount of, the vanishing gradient, what they explicitly proposed was this type of additional bit, okay? And this f of t is meaning that forget bit, okay? So if they are becoming one, then that we will, not counting those bits to the further process. And if this is, estimating zero, then we will count that for further processing. So we are estimating this type of forget, this type of how to say, the flag to retain or forget some of the information explicitly, okay? Because there are sigmoid at the last layer. They are basically applying the linear layer to the input and then applying the sigmoid, okay? So their output values are bounded to 0 to 1 value, okay? And they are meaning which will be retained and which will be forgotten, okay? And they are inputting current time element at the same time inputting some of the contextual information coming from the previous time, okay? And then apply the linear layer on the concatenated vector, and then apply the sigmoid, okay? And explicitly estimate what to forget. And another information we have to estimate is the I of t, and this is the bit for retaining, okay? So for some of the information we will retain, okay? And for some of the information we will forget. So we have to estimate 2 bit. And also we explicitly also transform the information and make this C tilde, okay? So this is some of the information we generate in this step, in this T time step, okay? This is the information we generate, okay? And I and F, that's some flags are estimated for which to forget, which to retain, okay? And this is the new, how to say, information. So this is the information we newly estimate from this time step, okay? And we multiply I of t, which is the bit for which item we will retain. And this is the forget bit multiplied with previous time steps information, okay? And by adding these two, we are making current times information again, okay? So this is the raw information, but we will only retain some of them. And also from the previous information, we will multiply f of t and explicitly lose some information. And then by adding them, making some new information, okay? And also, this is also the output bit, okay? The C of t, even for this information, we multiply again with the output bit to decide what to finally output, okay? So this is some internal information retained here, okay? So this is some internal information retained through the time domain. But this is the actual output, okay? So from the contextual information retained through the time, we multiply the output bit explicitly and to infer some output, okay? So at STM, they are having 3 types of bit, which is called as forget gate, input gate, and output gate. Okay, so they are controlling how much data we forget uh, from the past information and how much information we retain from the new information, how we use the new output. Okay, and by explicitly controlling this type of information, LSTM is becoming robust to the vanishing gradient phenomena. Okay. Are you guys following this? Maybe some of you already familiar to this LSTM and RNN. Okay. And okay, and next thing we have to see is using this type of LSTMs, we can do some translations. Okay. So for example, this is some sequence to sequence model that can translate the English sentence to the French sentence. Okay. This is the sequence to sequence model. And their input is sequence and the output is sequence. So they are called as sequence to sequence model. Okay. But I mean, their input and output is different. Okay. Given English sentence, we are wanting to generate some translated French sentence. Okay? And if we magnify the sequence to sequence model, that would look like this. Okay? And internally, they are having multiple LSTMs, maybe or RNNs inside. Okay? So this type of things are representative application in the NLP domain. And what they do in the encoder, they are also composed of the encoder and decoder architectures. And encoder, we call encoder for extracting features, and decoder, we call this decoding process as the generating the final output from the intermediate features. Okay. So the inputs are now the one-dimensional sequence, and the final output is also the one-dimensional sequence. Okay, and what they do is they input, they are one by one getting this word, the element of the sentence one by one, and using the LSTM, they somehow transmit the information, the each element information one by one, and the last information becomes the features. Okay, this becomes the feature for whole sentence. Okay, and then in the decoder, what they does is they are first inputting the starting tokens. Okay, start of the sentence. Okay, S2S. End of sentence, this is the end token. Okay. So at the first time, given this feature for one sentence, they are only inputting, their decoder looks like this, having just one LSTM. Okay. They only input this starting token, and then the decoder will decode the first word of the output. In French, I am a student, that's the English sentence, and this is the corresponding the French sentence, okay? And then they estimate only the first word of that output sentence, okay? And what happens next is, given these two, now because we estimate, this is very, you have to remember, so by inputting the first token, you estimate the first word, okay? And then we are having two input, the starting token, also the first word, okay? And by inputting these two as the input, we are estimating the next word, okay? And again, we are inputting this estimated second word as the additional input to this decoder, and then estimate the next word. We iterate this until we meet the end of sentence token. Okay, so this is the sequence to sequence model that composed of these LSTMs. Okay. Okay. And we call this sequence-to-sequence model as the autoregressive model because our output, estimate output, is becoming the input to next step. Okay, so we call this as the autoregressive algorithm. Okay. Anyways, this sequence-to-sequence model based on the LSTM have been the state-of-the-art algorithm before the transformer. Okay? Mostly the NLPs are done in this way. But when the transformer comes out in the year of 2017, this transformer is composed of the encoder and decoder architectures. Okay? And encoder, what they do is they are inputting this one-dimensional sequence data. I am a student. But opposite to, differently to this LSTM-based architecture, these architectures are inputting element one by one sequentially, but this transformer encoder, they are inputting all of the sentences at once. Okay? And what they do is they are applying attention mechanism. We will in detail see what is this attention mechanism. But basically what this attention mechanism does is they are, how to say, seeing all the pairs of this input. They are considering, uh, I mean, they are considering dense relationship, the dense pairwise relationships between the input. They are considering the relationship between I and M, and also I and A, I and student, and M and A, M and student, A and student, and calculate the features based on, encode the features based on this relationship. When calculating the relationship between I and M, they are somehow measuring their similarity in embedding space, and then multiply AM's feature to contribute in that way. According to that way. So when calculating I's feature, I word's feature, you are somehow weight summing AM's feature, A's feature, and student's feature according to their relationship between I and M, I and A, and I and student. Okay. Are you guys following this? Okay. So that's basically what happens in the encoder of the transformer. Okay. And also, what decoder does is similar to the previous sequence-to-sequence model based on the LSTM. What they does is they are sequentially, encoders are parallel processed. But decoders still have to be sequentially operated. So to say this is the feature encoded, and given this feature, they are only inputting the starting token and then estimate the first word. Okay? And in the next step, they are inputting these two as the input and estimate the second word. Okay? And again, inputting these three words, they are estimating the third word, and they iterated sequentially until they meet this end of sentence tokens. Okay, so that is happening in the decoder part. Okay, so encoders in transformer, the encoder is processed in the parallel manner, but decoder is still working in sequential manner. Okay, that's the transformer. And the other thing you have to also remember is in the transformer, uh, we use the positional encoding. Okay? So, in the encoder, even though there are some orders, okay? So, in this figure, there are orders. So it seems like we input I first, M later, and A next. student next. But in reality, it is not. So we are parallelly input these four elements, and there is actually no sequence, no order in the aspect of the encoder. Okay. So even you change, what I mean is here is if you input it in this way, there's no difference in the feature. Okay. In transformer, they are not knowing the input order. Okay. But this is not how to say ideal case for processing sentence data. So for example, I am a student and am a student A are two different sentences in for the humans. So we have to process this differently in transformer, but the naive, the simplest, I mean the simple transformer cannot deal with this differently. So that's why we are adding these positional encoding schemes. Okay? So these positional encoding schemes are what they does is very simple. So I is the first word. So they are making the same dimensional vector with the I embedding vector. And they are highlighting this first part because they are located in the earlier part of the sentence. And they are making the next positioning encoding vector for AM like this because that's the second element of the sentence and making it like this for the third word and making it like this, having the highest value in the last part for the student because that's the last word in the sentence. And then they are adding this positional vector encoding vector to the original word embedding vector, and then input it in this transformers encoder. Okay, and also that is also same for the decoder part. Okay, and this is something what actually happens in the transformer. Okay, that this positional encoded input vectors are now becoming new inputs to the transformer. And as I told you, this type of operations are actually the attention mechanism. Okay. Basically, you can think of this as when calculating the features for the student, you are making three types of vectors, okay, by multiplying some linear layers. So, I mean, this is the original word embedding uh, added with positional encoding vector, but you are transforming those vector, the original word embedding, to some features, and we will call that feature as query key values. There are Q, K, V, and we call that as query key value. Okay. And that's some intermediate, how to say, features, some vector to represent these word embeddings. Okay, and actually, these linear layers are the only parameters to be learned. Inside the attention mechanism, there is not much parameters, but we somehow have to learn the parameters for the deep architecture. And actually, these weight vectors are the parameters to be learned during the training. Okay, so for the CNN, we are learning the filter coefficients of the convolution operation, but in the transformer, we are training this weight vector that transform the original word embeddings. And then this QKV, what we does is uh, somehow Q and K, query and key, are multiplied to measure similarity between words. Okay, as I told you, uh, query and key, they are measuring some similarity between words. Okay, if I and I, their features are similar, then this will have the high similarity. And I and M, I am A, I am student, that those features maybe contributed depending on this similarity, and this value itself is becoming the feature for each word. And based on this similarity, each word's value features are contributed in the final feature. Okay, they are weight summed by this similarity to calculate the final features for the student, this original word. Okay, so for calculating the final feature for this student word, this Q and Q, how to say, query of student vector, they are weight, calculated, they are multiplied with key values of other words, and based on their similarity, other words' value features are added to get the final features for the student word. Okay, are you guys following this? Okay, that's the attention mechanism in the transformer, and you have to remember that this attention mechanism also composed of mainly the plus and multiplication operation, and these are parameters. So similar to convolution operation, because they are differentiable, having the differentiable operation, they can be embedded in the entire deep architecture to train these weight vectors. Okay, and also this is the transformer architecture that I mentioned, I explained previously, and actually this is the original figure drawn in the paper published in Eureps 2017, okay? And you have to understand these two figures are same, okay? So this part, sorry, this part is actually drawing the encoder part, and this part is drawing the decoder part. You have to understand that. And for the encoding, you will input the sequence, one-dimensional sequential data, and apply the input embedding first, and the positional encoding have to be added, and they are mapped to three different input, and that is actually meaning the key query values. Okay, so from this word embedding, positional encoded word embedding, you are mapped to key query values. That's three inputs to the attention mechanism here. And those kind of attention mechanism that I explained in previous slide is calculated, and then they are applied with feed folding layer, which is similar to the MLP layer. And this becomes the feature vector, okay, for the entire sentence. So, that is actually same as what happened in this encoding part, okay? So, this part you have to understand is same component as this encoder in this figure, okay? And then now the final output of here is meaning the same thing as this, which is the feature for the entire sentence, okay? And in the decoder part, you can see this type of shifted right, okay? So this means the sequential operation. So in decoder, I mentioned that the first time this starting token only was applied to estimate the first element, and then this is inputted again and estimate the second word. Okay, sequentially the decoder works. Okay, and this is meaning that kind of thing. Okay, So they are applied actually sequentially, and they are encoding the output word, okay, and apply the positional encoding, and also apply the attention mechanism by transforming this, how to say, this output input, these decoder inputs are also, uh, one time applied with the attention mechanism, okay? And the other important component in transformers you have to understand is uh, these two attention mechanism, these orange blocks are representing the attention mechanism in the transformer architecture. So these three blocks are colored with orange color, and they are all representing the attention mechanism that I mentioned. So they are basically inputting key query value, and they are calculating the similarity between input and getting the final feature by adding them. But the thing is, these two attentions are called as self-attention mechanism, but this part is called as cross-attention mechanism. You have to remember this. The thing is, these two attention mechanisms are inputting the same signals as the key query values. Okay, so it's very simple to notice this. These two parts, the key query values are coming from the same source, which is the input to the encoder and which is the input to the decoder. Okay, but this part is called as cross attention because some of their inputs are coming from the encoder's feature, and some others are coming from the previous decoding layers. Okay, so because their inputs are coming from the heterogeneous input, they are called as the cross attention mechanism, and they are coming. Their inputs are coming from the same source. They are called as self attention mechanism. In this attention mechanism, they are somehow mixing the encoder features with the decoder's previous layers features, okay, which is the input to the decoder inputs embeddings. They are somehow mixing those two information in this cross attention, okay, and then further apply the MLP and finally map it to the output, okay. So are you guys following this? Okay. So this is the transformer architecture actually for the one-dimensional signals actually in the NLP domain. And this is some extension of the transformer algorithm. So far we learned that the key queries are how to say multiplied and value is added. Okay, so that's the attention mechanism, original attention mechanism, but we can extend it to have multiple how to say attention mechanism in one attention layer. Okay, so we normally have the same key query values are fed into multiple attention mechanisms. Okay, but the thing is, they will have multiple linear layers. So they are somehow transforming the input into the different way and then apply the attention mechanism. And after that, they are concatenating all the attentions output here, and then apply another linear layer to merging those information. Okay, and then this becomes the final output. Okay. So this is the simple extension of the multi-head attention, but having better final accuracy. Okay, so we normally use this multi-head attention. So in this slide as well, If you see those blocks in detail, then you can see they are called as multi-head attention. Okay, they are having multi-heads. Okay, their basic blocks are attention, but they are having multiple attentions, and then concatenate their output and apply another linear layer to merge them. Okay, to produce the final robust output. That's the transformer architecture. Okay, so the transformer, their encoders are non-sequential, so they can process as a whole rather than word by word. So the sequence-to-sequence model composed of the LSTMs are processing feature encoding in the sequential way. So transformer, they can be robust by processing them in the parallel way. And also, no risk to lose the past information. LSTMs are improving the RNN, but still have some issues in losing some past information. Okay, but transformer, as it can process those inputs in parallel way, uh, they can be safe for losing the information, and also they can allow the parallel processing. So this is the some of the reasons why transformer are better than the LSTMs. Okay. Next, so far we learned about transformer architecture in the NLP domain. But next, we will see how these transformers are applied in the computer vision domain to deal with image classification and object detection tasks mainly. Okay. And the first architecture we have to see is this Vision transformer. Okay. In the year of 2021 ICLR conference, this VIT has been proposed. So in the next lecture, we will see what is happening in this Vision transformer, VIT. Okay. And also we will see how we can achieve the object detection task using the transformer-based approach. Okay, and this is the earlier. So actually, for the VIT appeared in 2021, but in the year of 2020, DTR appears, which is the first transformer-based object detection algorithm. Okay, we will see how it works. Okay, as well. But there has been some slide. So this is the transformer in the NLP domain. This is the transformer architecture for the computer vision domain, especially for the object detection task. Okay, so we will see which type of things have been changed. Okay, to apply transformers in the vision domain. Okay, so for today, maybe we can finish here. Thank you. See you Wednesday.